All right, let's talk about a piece of technology that's almost certainly inside the very device you're watching this on. And yet, for most of us, it's a complete mystery. It's called electroless plating. And believe me, it's a revolutionary process that's quietly changing everything our materials can do.
I know. It sounds like something straight out of science fiction, right? How can you possibly give an object properties it was never meant to have? Well, the answer lies in this really clever chemical trick that lets us coat pretty much any material with a perfect, uniform layer of metal. And the results? They're creating a whole new generation of smart materials.
So, how does this magic actually work? Well, to really get what makes electroless plating so special, it helps to take a quick look at the old-school way of doing things. So on one side, you have traditional electroplating. You run an electric current through a liquid to stick some metal onto something. It works, sure, but it's not great with complex shapes, and it only works on stuff that can already conduct electricity. But then you have electroless plating. This is a whole different ballgame. It's a self-catalyzing chemical reaction, no electricity needed. And that means it can coat anything, plastics, ceramics, even fibers, with a perfectly even layer of metal, no matter how weird the shape.
What it really boils down to is this. A controlled chemical bath does all the heavy lifting. By ditching that external power source, we unlock this incredible ability to metallize materials that used to be completely off-limits. We're creating these amazing new hybrid materials. But getting that metal to actually stick, well, that's where the real genius is.
So yeah, how do you make the metal stick? It turns out the biggest challenge isn't the plating itself. It's all about preparing the surface so that shiny new metal layer doesn't just flake right off.
Think about it like this. Ever try to paint on a super slick, glossy piece of plastic? The paint has absolutely nothing to grab onto. It's the exact same problem here. Materials like aramid fibers or these advanced polymers, they're chemically inert and incredibly smooth. So before you can even think about plating them, you have to give the metal something to grip. You need a kind of primer, but on a microscopic scale.
And the process, when you break it down, is surprisingly straightforward. First, you clean and prepare the object. Then comes the most important step of all, surface activation. This is where you create those microscopic anchor points. And finally, you just dip the object into the chemical bath, and the metal coating forms perfectly. That middle step, surface activation, that's where all the cool, cutting-edge science is really happening.
So let's dive into the really cool part, the high-tech toolkit that engineers are using for that activation step. And believe me, this is way more advanced than just some simple chemical wash.
First up, we've got lasers. This is one technique called selective surface activation induced by laser, or SSAL for short, which basically lets engineers draw circuits directly onto 3D printed parts. The laser precisely carves this little path, creating a roughened, chemically receptive trail for the metal to grab onto during the plating process.
The advantage here is just incredible precision. We're talking about creating fully functional 3D electronic circuitry on the most complex shapes. This is already being used to create super strong nickel films on carbon fiber composites for, next generation aerospace parts and microwave components.
Okay, next up in the toolkit is something truly wild, supercritical CO₂. At a very specific temperature and pressure, CO₂ enters this weird hybrid state. It's kind of like a liquid and kind of like a gas at the same time. This turns it into a perfect stealth delivery system. It can carry the metal catalyst deep into the pores of a material, like a fabric, without causing any of the swelling or damage that harsh chemicals would. And this is a total game changer for creating flexible, weavable electronics. Using this method, researchers can plate advanced polymers like PET, the plastic in water bottles, or even the super strong polyethylene fibers used in body armor. It literally turns them into conductive threads while keeping all their original strength and flexibility. It's amazing. And finally, we have plasma. Now, don't think about heat or sci-fi weapons. This is about using an energized gas to basically bombard a surface. What this does is etch a really complex, nanoscale landscape onto the material. It transforms a perfectly smooth surface into one with countless microscopic peaks and valleys that the metal can physically lock into, creating this unbelievably strong bond. What's so remarkable here is that this creates phenomenal grip without actually making the surface feel rough. And that is absolutely vital for things like the high-frequency flexible circuits you'd find in advanced displays. They're often built on something called pen films, where you need a smooth surface to keep the signal clean. Plasma gives you that grip without causing any interference.
Okay, so we've got lasers, supercritical fluids, and plasma. That's the how. But what about the why?
Let's connect these incredible techniques to the next generation of materials they are creating right now.
I mean, the impact is just so diverse. We can take 3D printed steel and literally double its scratch resistance. We can pleat textiles with silver to create these e-fabrics that aren't just conductive but also antimicrobial. This tech is turning polymer fibers into flexible circuits and making graphite composites even stronger and lighter by improving the bond between the graphite and copper. So just how strong are these new bonds? Well, get this. One recent study that combined plasma treatment with a special titanium layer achieved an adhesion strength of almost 1,400 gram force per centimeter. Now, to put that in perspective, that's like hanging a bag of sugar from a tiny strip of this material that's only 1 centimeter wide. It absolutely shatters the existing industry standards. This isn't just a coating anymore. It's becoming a part of the material itself.
So, the big takeaway here is that we really need to stop thinking of plating as just a shiny finish. These advanced techniques are turning it into a foundational manufacturing tool. It's a way to build brand new hybrid materials from the ground up, combining the best properties of things like plastics and fabrics with the incredible functionality of metals.
Ultimately, what these methods are doing is turning passive, everyday materials into active, functional components. And that really begs the question, what does our future look like when your clothes or the walls of your house or any object you can 3D print can be embedded with the power of metal? What will we build when literally anything can become a piece of technology?